Hello class, welcome to this lesson on 6.1. We're going to be talking about key features of exponential functions. So we're going to be starting a brand new unit talking about a brand new set of functions, the exponential function. So how do graphs and equations reveal key features of exponential growth and decay functions? So we want to be able to recognize key features of exponential functions such as asymptotes, end behavior, domain, range, and intercepts. We're also going to be talking about the decay rate and growth rate. So we're going to talk about decay factor, exponential decay function, growth function, an exponential function, and growth factor. So an exponential function is any function of the form y equals a times b raised to the x power, where a cannot be 0, b has to be greater than 1, and b cannot be equal to 1. So an exponential function can be thought of as a function that shows a steep decrease or increase over time, depending on the rate of growth or decrease. So there's a lot of examples of exponential functions, including, in finance, including when you're buying a car, you're talking about loans, you're talking about compound interest. There's so many examples of exponential functions. So we're going to be talking about the graph of an exponential function first and the key features. So we're going to talk about domain, range, intercepts, asymptotes, and the end behavior. So let's say we wanted a graph y equal to 2 to the x power. So first what we're going to do is we're going to actually set up an xy table for both. We're going to plug in the numbers from -2 to 2. So let's start by plugging in the x coordinate into the function, the -2. So if we plug in -2 into our y coordinate, into our y, we got 2 to the -2 power. Just like that. But remember that a negative exponent means that you flip and forget. So you're going to flip this down. This becomes 2. This is the same thing as 2 over 1. So you're going to flip it, and it becomes 1 over 2, and then you forget the sign. So it'd be to the +2 power. And we know that 2 to the second power is 4, so this becomes 1 over 4. Again, if we repeat for -1, you're going to plug that in. You get 2 to the -1 power. But since that's a negative exponent, you flip and forget. So it's going to be 1 over 2 to the +1 power. Now 2 to the 1 power is 2, so we get 1 over 2. If you plug in 0, you're going to get 2 to the 0 power. And anything to the 0 power is 1. Now if you do 2 to the first power, that's going to be 2. And if you did 2 to the second power, that's going to be 4. So we got our coordinates here. So now let's go ahead and do our coordinates for the next function. So we have 5 times 1/2 to the x power. Okay, so again, let's plug in the -2 into the function itself, right? So we have 5 times 1/2 raised to the -2 power. Again, since we got a negative exponent, we're going to go ahead and flip and forget. So this becomes 5 times, we're going to flip the 1 over 2, now it's going to be 2 over 1, which is the same thing as 2, but I'm going to write it as 2 over 1. And then now we forget the sign, so it's going to be squared. So we know that 2 squared is 4, so we have here 5 times 4 is 20. Now let's go ahead and plug in the -1. So we have 5 times 1/2 to the -1 power. Again, since there's a negative exponent, we flip and forget. So we get 5 times 2 over 1 to the first power. Well, 2 to the first power is 2, and then 5 times 2 is 10. Now let's do 5 times 1/2 to the 0 power. Remember, anything to the 0 power is 1. So we have here 5 times 1 is 5. Now we're going to do 5 times 1/2 to the first power. 1/2 to the first power is 1/2. So we have 5 times 1/2, which is 5 halves. And lastly, we have 5 times 1/2 to the second power. 1/2 to the second power is 1/2 times 1/2. 1/2 times 1/2 is 1/4. Or you can just distribute the 2 here and here, and then that'll give you 2 squared is 4, and then 1 squared is 1. And then 5 times 1/4 is 5 over 4. Alright, so those are going to be our values. Alright, so we went ahead and replaced those values. This time I used decimals instead of fractions. So again, I got this to be, this is the same thing as the number that I got earlier, 5 halves, and then this is the same thing as 5/4. All right, so now we're going to go ahead and do the graphs here. So now we're going to go ahead and plot the coordinates. Now that we have the coordinates here, we got 1, 2, 3, 1, 2, 3. All right, so for this one, we have when x is -2, y is pretty small, 1/4. That's 0.25. And then 1/2 is 0.5. Okay, so when x is -2, we got 0.25, which is pretty small. When x is -1, you get 0.5, so about a half. When x is 0, you get 1. When x is 1, you get 2. And when x is 2, you get 4. All right, so we're able to go ahead and draw the graph here. So what's happening is that on the left side is getting smaller and smaller and smaller, but it's actually never approaching 0. So this side actually never, right here, it never touches, I guess, the x-axis. So it does not touch the x-axis on that side. So therefore, it can never actually cross the x-axis, so there is no x-intercept here. All right, and then it's clearly going up on the right side. Now we're going to go ahead and draw the graph here for the right one. So when x is -2, you get a y value of 20. So I'm going to go ahead and go by 2's here. And 20. Okay, so this is going by 2's. All right, so when x is -2, we get 20. When x is -1, you get 10. When x is 0, you get 5. Very small. X is 1, you get 2.5. When x is 2, 1.25. All right, so then we can clearly see, now I'm going to go ahead and erase these points just because I want to go ahead and actually show the graph here. All right, so notice again, it's not approaching, on this side is never touches the x-axis. It never touches the x-axis on that side. So it's getting smaller and smaller and smaller, but never actually crossing the x-axis. All right, so we got our two graphs. Now let's go ahead and do our domain and range. So the domain are the x values. So looking at this graph, we have all the negative x values and we have all the positive x values. Remember, x is that axis. So that means that we have all the x values covered, which means that our domain is -infinity to infinity, or all real numbers. Same thing with the right side. We got all the negative values for x. We got all the positive values for x. So therefore, we're all covered. It's from -infinity to infinity. Now the range is going to be from the x-axis upward. So therefore, the smallest y value is y equals 0. And then it just goes up from there if you look at the graph. So therefore, my range is from 0 to infinity. And we're not going to include the 0 because this never touches the x-axis. So therefore, we're going to put a parentheses, not a bracket there. Or you could just say y is greater than 0. All right, same thing for here. You know, the smallest that y gets is 0, and then it just goes up from there. So we have, you could do 0 to infinity, or you could do y is greater than 0. Now for the y-intercept is where it crosses the x-axis. So the only spot it crosses the x-axis is here. So that's my y-intercept. So my y-intercept is y equals 1, and my y-intercept here is y equals 1.25, which actually is going to be 2.5, not 1.25. So it's going to be 2.5, and that's because of this, this. Actually, it's not even that. I apologize. It's this right here, 0, 5. I messed that up a couple times. So y equals 5. And then for this one, the left side, y equals 1, because if you look at the coordinates, that's when x is 0, when y is 1. So this is the y-intercept here. Okay. Now the asymptote is where the graph approaches but never actually crosses, right? So it looks like the asymptote is here, right? Because it never actually crosses that asymptote. So same thing for this one. It actually never touches that spot right there. So therefore that is an asymptote when it's trying to approach it. So in this case the asymptote is y equals 0, which is the x-axis. Same deal here, y equals 0 for the asymptote. In this case, this is a horizontal asymptote. There are no vertical asymptotes for exponential functions, just horizontal asymptotes. All right, now let's talk end behavior. So for end behavior, remember that the way to do end behavior is the infinity notation, right? So as x approaches positive infinity, the graph is actually going up. So as x goes to positive infinity, y goes to positive infinity. So that's our first part. So as x approaches positive infinity, y gets bigger and bigger. As x goes more negative, so in this case, as x goes more negative, this time going that way, the graph is not going up anymore. The graph is actually going down, right? So you're actually going down to what value? Well, it's going down to 0, right? But never actually reaching 0. So as x is going down to the left, the graph is decreasing to 0. So as x approaches negative infinity, y approaches 0. But of course never reaches it. All right, now for the end behavior on the right side, as x approaches negative infinity, the y approaches positive infinity. So as x goes negative, y approaches positive infinity. As x approaches positive infinity, so what happens as the graph goes to the right? Well, as the graph goes to the right, positive infinity, the graph is actually going down, right? It's going down to 0, the x-axis. So as x approaches positive infinity, y approaches 0. So you got to practice those, that kind of end behavior. All right, so now notice that g of x and f of x were actually, that g of x is actually the transformed version of f of x. So let's show you why that's the case. So we're going to transform f of x so that it looks like, or g of x so that it looks like f of x. So how do we do that? Well, let's go ahead and leave the 5 there alone for a second. Now what happens if I go ahead and flip this fraction so that it becomes 2 over 1? Well, if I flip it, I need to introduce a negative exponent. Why? Well, remember that when you have a negative exponent, that means you flip and forget. So that means you'll end up going back to this original, right? So, but we want to put it in this form because now we can clearly see, well, hey, this is in terms of 2. So what that does, well, what are the transformations? The transformation is, since the parent function is 2 to the x, well, what does that do to 2 to the x? Well, remember, this is how 2 to the x looked like, right? That's how 2 to the x looked like when we graphed it. So what does a negative do right here? Well, the negative actually reflects it. So we have a reflection around or about the y-axis. So remember that if x is negative, it flips it about the y-axis. So basically it flips it so it looks like, this, right? And then what does the 5 actually do? Well, the 5 actually just stretches it, right? So the 5 multiplies it by 5. So it just stretches it out, and it stretches it vertically. So this is a vertical stretch by 5. And those are my two transformations. So what that does, it just stretches it out, so it's more like this. Now that should look familiar because it did look like that when we looked at the original, the second graph. So let's go ahead and illustrate that. So this is the original, this is the reflected version, but stretched. How do we know it was stretched? Well, this number here is 20, which is really big, compared to this number here, which was, originally 8. So definitely going to be a stretch there, and definitely reflected. So we can think of f of x as the parent function. This is actually an important point here. So we're going to actually identify the parent function given the new transform function, and then we're going to actually graph it using the idea of the parent function. So it says to graph each function, describe the graph in terms of transformations of its parent function, find the asymptote of the function. All right, so the parent function for this is g of x equals 3 to the x. So that's the parent function well, we'll just call this f of x. So that's the parent function is 3 to the x. So how do we know it's 3 to the x? Well, there's just a negative there. So the negative just does a reflection. Remember that this negative reflects. Reflects about what? In this case, it reflects about the x-axis. How do I know it reflects about the x-axis? Well, when you do a table for this, remember that this is the parent function, right? So you can think of this as y. So the y prime, the transformation here in the y is negative y. You can think of this as y prime. So the transformation is negative y because the negative is on the outside. So therefore, this is a negative in front of y, which means it's a reflection about the x-axis. It's the opposite of what you think. All right, so then now, since we know it's a reflection about the x-axis, and I know that 3 to the x, how do I know what 3 to the x looks like? Well, it's actually pretty simple because remember that if you were to plug in these numbers, right, -2, -1, 0, 1, 2, you could do that real quick, and it doesn't take very long. 3 to the second is 9, so you get 3 to the second is 9, 3 to the first is 3, 3 to the 0 is 1, 3 to the -1 is 1 over 3, and 3 to the -2 is 1 over 3 squared, which is 1 over 9. Remember the flip and forget. So this function looks identical, looks pretty similar to the 2 to the x function, but it just grows faster. So this function still looks like this. In fact, this is how all parent functions are going to look like. They're going to look like this, except, depending on the number here, the 3 or 2 or 4, it'll grow faster. So in this case, it'll always start at 1. It'll always have a y-intercept of 1. And in this case, since the numbers are different, because instead of it being 4 here, it's a 9. Okay, so when x is 2, y is going to be 9 instead. And when x is 1, y is going to be 3. So the numbers there are different, but the graph is the same. The graph is identical. So now all you got to do is reflect that graph. So if I reflect that graph about the x-axis, well, then it's going to look like this. And that's how my g of x looks like. So then what's the asymptote? Well, the asymptote in this case is still going to be the x-axis. So the asymptote is going to be y equals 0. It's still going to be y equals 0. And that's it for our graph. All right, now what's the parent function of this guy? Parent function of this guy is 4 to the x. That's it. That's the meat of the function. The rest is just transformation. The minus 4 just transforms it. What does the minus 4 do? Well, the minus 4 is just a transformation, so it's a y prime transformation. So it basically transforms it so that you could think of this as y, so it'd be y minus 4. So it's just a y transformation. So it just basically it just shifts it down by 4. So this shifts down by 4. All right, so then all you got to do is take the parent function, which we know looks kind of like this, right? The only difference is now when x is 1, you're going to get 4. That's the difference. And when x is 2, you're going to get 16. So it just grows faster. It grows pretty fast. Of course, you know, this is not to build to scale, right? And then to do shift down by 4, well, now this is going to be shifted down by 4. So if this is going to be 1, then now it's going to be down 4. So it's going to be down at a negative 3. Okay. Now, if the original asymptote is at y equals 0, well, then if I shift that down 4 units, right? If I shift that down 4 units, 1, 2, 3, 4, well, my new asymptote now is going to be y equals negative 4. So that's my new asymptote now. That's the one thing that changes that's different is that the asymptote changes. So it's y equals negative 4 is my new asymptote. So it's really not too bad. So if you got a minus on the outside or a plus on the outside, you're shifting it up or down. If you have a negative on the outside, you reflect about the x. If you have a negative on the exponent, then it's reflecting about the y. If you have a number added to the exponent, like say x plus 2 power like this, then that's going to shift it either right or left. All right, pause the video, try the following problems. All right, so we want to graph each function and do the parent function, the whole deal. So let's go ahead and identify the parent function first. So the parent function here is simply 5 to the x. Right, pretty simple. So now, what does the x plus 3 transformation do? Well, remember that in order to do the ExPrime transformation, we usually set the inside, right, equal to x prime, and then solve that. So really, if you were to subtract the inside, in this case is like the exponent, right? That's what I call the inside, right? So we set that inside equal to x plus 3, and then x prime, and then we solve for x. So we get x prime minus 3 equals x. All right, and then now this is my transformation. So now I know that you got to take the x and we got to subtract 3, which means it really is a shift to the left, okay? So this means it's a shift left by 3. So that's what it does. It just shifts it left 3. Now we know that the parent function looks like this, right? Where when x is 1, y is 5, because 5 to the 1 power is 5. When x is 0, y is 1. When x is 2, y is like 25. So it grows pretty fast, right? When x is 2, then you get y is 25. And then what we're going to do is we're just going to shift that left by 3. So in this 1 now will be shifted to the left by 3. So it'll be 1, 2, 3. Same deal here. And then once we shift everything by 3, we'll have something that looks like that. So now I'm going to go ahead and erase the jumps, and there's my new graph. So now everything is shifted to the left 3, but the asymptote is still the same, right? The asymptote actually doesn't change. So the asymptote is still going to be y equals 0. All right, now we're going to go ahead and, oops, yes, we're going to do 3 to the negative x. So the parent function for this is f of x equals 3 to the x. That's all. So now that we got the parent function, what does the negative do? Well, the negative is in front of the x, right? So that means so if you got a negative in front of x, so if x were to be 2 and you made a negative 2, well, then that means you flipped it. You flipped it about the y-axis. So this is a reflection about y. So reflection about the y-axis. All right. So since it's a reflection about y, all we got to do is draw a parent function, which looks like this, and we're going to reflect it about the y. So it looks something like that. Now normally when x is 1, this is going to be 1, but when x is 1, y is going to be 3. When x is 2, y is going to be 9. And there's our guy. So our graph is given in red. Now notice that the asymptote is still going to be the same. The asymptote is still going to be y equals 0. Since it didn't shift up or down. All right, so now lastly, we're going to talk about exponential growth and exponential decay functions and what they represent. So exponential growth and decay functions model quantities that increase or decrease by a fixed percent during each time period. So basically, you're given an initial amount, A, and you're given the rate of increase or decrease, which we call R. And then, so we end up figuring out the amount after a certain period of time, usually, T for time. So here's the growth and decay function. So basically, A of t is a times b raised to the t. Remember that the exponential model was a times b to the x? Well, this time we're using a times b to the t, where b is equal to 1 plus r. So I'm going to go ahead and make this a blue b so that you can kind of tell that it's based off of the 1 plus r. All right, so, and then same thing here. A of t equals a times, this time I'll make this a red b to the t, so that we can compare it to the red 1 minus r. All right, so basically if its exponential growth is 1 plus a number, right, 1 plus the rate, if it's decay, it's 1 minus a rate, which kind of makes sense. So in this case, for it to be exponential growth, the b has to be greater than 1, like for example 2 or 3 or 4. For decay, the b has to be between 0 and 1, so meaning a fraction that is smaller. So the growth or decay factor is called b, or 1 plus r, or 1 minus r. All right. Now the growth factor is the ratio between two consecutive y values. So what that means is, like, for example, if we have, let's say we got a set of data and we got 4 and 8 and 16, something like that. Well, we know that this is multiplying by 2. So since it's timesing by 2, my growth factor is 2 in this case. So in this case, b is 2. So that's what that's saying, that the b is the ratio between the consecutive y values. So basically 8 divided by 4, which is 2. That's what that means, the ratio between the two consecutive values. But we don't really need to worry too much about that. What we really want to know is how to determine if something is a growth or a decay factor, or exponential growth or decay. That's really what we want to know right now. So here are some examples. Y equals 3 times 0.7 to the x power. Now 0.7 to the x power, that's my b. And my b here is less than 1, but it's also greater than 0. So my b here is a fraction. Therefore, this is going to be exponential decay, since that b is smaller. Now looking at the next example, y equals 2 times 1/3 to the x power. Again, this is b. Now b here is 1/3, and 1/3 is less than 1 but greater than 0. So this is going to be also exponential decay. Lastly, y equals 2 times 3 to the x. So this is my b. And now here my b is clearly going to be greater than 1. So this is going to be exponential growth. So just look at the b. If the b is between 0 and 1, then it's decay. If the b is greater than 1, it's considered growth. All right, so we're going to actually look at another example. This is actually a very common example. You're purchasing a car for $24,000. So let's say you purchase a brand new car. Now the function y equals 24 times 0.8 to the x can be used to model the value of the car in thousands of dollars, x years after it was purchased. So basically, you start out with $24,000. That's what this number is here, 24. And basically, it's, it's given by this function. So like, let's say you bought it for, 5 years after it was purchased, then you plug a 5 in here, and that will tell you what the value of the car will be. Now we know from experience that the value of the car is going to diminish over time, right? So 5 years after you purchase it, it's going to get older and it's going to diminish in value. So it's going to decrease in value. So does this function represent growth or decay? Well, it's definitely not going to be growth. It's definitely going to be decay, since the value is diminishing over time. Now you can also tell that from the value here, the b, right? The b here is between 0 and 1. So this is definitely going to be a decay. So this is exponential decay. Now what is the rate of decay for the function? So the rate of decay, remember that the rate of decay b is 1 plus r or 1 minus r. So in this case, decay is minus, so it's 1 minus. All right, so what is b? Well, b is 0.8, right? So the only way we can get 0.8 is if r is 0.2. So r has to be 0.2, since 1 minus 0.2 is 0.8. Okay, so my rate of decay is 0.2. This is my rate of decay. Now, what does this mean? Well, this means that the rate of decay is 20%. So this is the decay rate is 20%. This means this is how much the car depreciates. You guys know the word depreciate. So 20% is the depreciation rate. So this is the rate at which the car depreciates in value. So that means the value of the car is going down by 20% every year. Okay, so this is an actual practical example of using exponential functions. In this case, when you're buying a car. So you got to consider that generally it's not very wise to buy a car that is brand new. And the reason why it's not wise to buy a car that is brand new is because of the depreciation rate. If you buy a car that's $24,000, then as soon as that year passes by, you lost 20% of its value. So therefore, that's 24,000. So if you were to do 20% of 20,000 or of 24,000, that's $4,800 right off the bat for that 1 year. So you lost a lot of value in the car. However, if you buy a car that's used and not as expensive, then you lose a lot less value. So let's say you bought a car that was used, that's still in good shape, but it was used for $10,000. Well, in that case, you're only going to lose about $2,000, which is a lot less than the $4,800. Now, this makes a difference because you're losing less value, which means you're still going to be able to sell the car if you wanted to sell it and get another car for roughly the same price, because the diminishing returns actually decreases. So it's something to keep in mind when you're thinking about life choices. All right, guys, that's it for the video. I hope you learned something new, and I will see you in the next one.